Welcome back. This is going to be the third example of analyzing the graph of a function, also called curve sketching. So this time I have your favorite. I have a trig function for you. So we want to discuss, remember the guidelines, we're going to find the x-intercept, the y-intercept, the vertical asymptotes, the horizontal asymptote, the first derivative so we can find increasing, decreasing, relative max, relative min, the second derivative so we can find concave upward, concave downward, inflection points, and any of those other odd things like does it cross a horizontal asymptote, does it have a slant asymptote. So the first thing I want to do for this one though, and I should do this pretty for every single problem we look at, we need to find the domain, the original domain of the function. Usually this is done kind of in the middle of a problem, but with a trig function we might need to take a closer look. So we've got g of x equals x times the cotangent of x. And if you'll notice, whenever you're given a trig function, you're given an interval as well, because trig functions are periodic, right? They repeat. And so if you are not given an interval to look at and you're looking at negative infinity all the way to positive infinity, the problem is going to be your chart that you do, say for the first derivative or second derivative, is going to be infinite, more than likely. So it has to be narrowed down so we get a picture just of part of the graph for trig functions. And we want to look at the domain. Okay, what values are we allowed to substitute into this function? Now most folks don't look at cotangent, tangent of x, secant of x, and cosecant of x very well to think about the domain. You may want to convert that to sines and cosines. So another way to write this function is g of x is equal to x times the cosine of x. Stand by while my computer catches up. Cosine of x divided by the sine of x. Okay, so this is equivalent function, but this is easier to tell what the domain is. And remember, when you find the domain, what you're really concerned about is if it has a square root, you can't take the square root of a negative number, which this clearly doesn't have, or does it have a denominator? Is there a place where the denominator is equal to 0? And sure is in this case, right? There is a place where sine of x is equal to 0. And where would that be? Okay, well, x equals 0. If you plug 0 into sine of 0, that gives you 0. Where else? Well, how about x is equal to pi? X is equal to 2 pi. What about negative values? How about x is equal to negative pi and x is equal to negative 2 pi? And of course that happens an infinite number of times, but we're only looking at between negative 2 pi and positive 2 pi. And notice there's no equal to. We're not looking at these endpoints. So this function is undefined at x is equal to negative pi, x is equal to 0, and x is equal to positive pi. We need to keep that in mind because when we do our charts for the first derivative and second derivative, we're always going to have to consider intervals with these values taken out. Okay, so let's keep in mind what our domain is. So everything from negative 2 pi all the way to negative pi, then we'd have to split it up from negative pi to 0, split it up from 0 to pi, and then finally from pi to 2 pi. Okay, so keep that in mind. That's just our domain. So now our next order of business, x-intercepts. Now remember how to find an x-intercept. You set y equal to 0, or in our case, g of x equal to 0. So I set this entire function 0 equals x times the cotangent of x. That's what I'm solving. Now again, it may be easier to think about this in terms of sine and cosine, but notice first, before we do that, this is factored. So I set x is equal to 0 here, this factor equal to 0, and I set cotangent of x equal to 0. Now this is a solution, but if you'll remember in the previous page, this function is not defined at 0, undefined at 0. So this is not really an x-intercept, okay? It's out because the function is undefined there. And that's why it's always a good idea to address where the function is undefined before we do anything else. Matter of fact, we probably just need to add that to our guidelines. Guideline number 1, what is the domain of the function? What about solving cotangent of x is equal to 0? Well, cotangent we know is cosine of x divided by sine of x, just by definition. Now to solve an equation, you know what you do. The first thing is you multiply both sides by any denominator, because you need to remove the any variable from the denominator. So those cancel, and I get cosine of x equal to 0. Another way to think about that is the only way a fraction is equal to 0 is if the numerator is truly equal to 0. Now, where is cosine of x equal to 0? We know that cosine of x is equal to 0 at x is equal to pi over 2, right? Also at x is equal to 3 pi over 2. But what if you go backwards around the circle? Well, negative pi over 2, which is in the same location as 3 pi over 2, and negative 3 pi over 2 is in the same location as pi over 2. So if I made my list, and preferably in order, my x-intercepts are negative 3 pi over 2, comma 0, negative pi over 2, comma 0, positive pi over 2, 0, and finally 3 pi over 2, 0. So I have 4 x-intercepts, and that's them listed in point form. You could also list them just as a list of x values. So I got 4 x-intercepts. And again, remember that x equals 0 didn't work because sine of x equals to 0 happens at x equals 0, and that's where my function is undefined. Okay? Anything else on this list give you undefined? Like sine of negative 3 pi over 2, is that okay? Yeah, it's fine, right? Sine of negative 3 pi over 2 is 1. Sine of negative pi over 2 is negative 1. Sine of pi over 2 is positive 1, and sine of 3 pi over 2 is negative 1. So that's fine. Those are fine, okay? It's, again, x equals 0 that's an issue. Well, let's move on to y-intercepts then. So remember, a y-intercept, that's always the easier of the two intercepts to calculate because you're just setting x equal to 0. And when I plug x into this function, 0 into this function, my bad, g of 0 is equal to 0 times the cotangent of 0. Now, your first thought is that's 0, right? But remember, x equals 0 is not even in the domain. We're not allowed to plug in 0. Again, argument for finding the domain before you do anything else. You can't substitute x equals 0, therefore there is no y-intercept. Again, you catch that? It's because x equals 0 is not in the domain. Now, would you have found it here? Well, sort of. If you're too quick, you would say 0 times anything is 0. So you would get 0, 0 as an answer. But careful, this is 0 times the cotangent is the cosine of 0 divided by the sine of 0. And this is undefined. Trig functions, you got to be super careful. So let's keep cruising through our list. And the next thing we need to find are vertical asymptotes. Now, vertical asymptotes happen when you get plus or minus infinity when you take the limit approaching a particular value. But now you've got to find that particular value. So essentially what you're doing is you're finding out where the function is undefined, but after you simplify. So always remember to simplify the function first, if needed, and then determine where the function is undefined. Now, y'all, this function doesn't really simplify. So I'm just considering g of x is equal to x times the cosine of x over the sine of x. Notice how I keep changing it back to sine and cosine format because that's the true way to tell where the function is undefined. We've already done this. Remember when we found the domain and we just set the denominator equal to 0? We already know where this function is undefined. Now, since it didn't simplify beforehand, those are also going to be vertical asymptotes. So we're going to have a vertical asymptote at, remember what they are? What makes the denominator 0? That's negative pi, 0, and positive pi. So those are my vertical asymptotes. Now, one more thing that would be super helpful, and this is where all the work comes in with vertical asymptotes, is determining the behavior of the graph at those 3 asymptotes. So it's like 6 limits we need to find. We need to find the limit as x goes to negative pi from the left side, and the limit as x goes to negative pi from the right side. Okay, then we'll do that with 0. We'll find the limit as x goes to 0 from the left side, and the limit as x goes to 0 from the right side. And then finally, the limit as x goes to pi from the left side, and the limit as x goes to pi from the right side. Now, here's what we already know. We know the answer is either plus or minus infinity, because that's what happens when you have an undefined situation, okay? And that's what we have. We've got to determine which one it is. And so whenever that's the case, that's when I play with signs, okay? So here's the fun. If I'm going to negative pi from the left, remember I'm plugging in that negative value right here, okay? So negative pi on the left side of negative pi, remember negative pi is about negative 3.14. Well, to the left of that is even more of a negative number. So we're definitely negative when we plug into just x, okay? Now let's plug into cosine. Now picture either the unit circle or the graph of cosine, but to the left of negative pi, okay? So you're talking about negative pi means the angle is negative. You're going backwards around the circle, or you can picture the graph of cosine. That may be easier. You know, the cosine graph looks like this, okay? And those are pi over 2 values, okay? And that's negative pi and that's positive pi. And then the graph of sine looks like this, okay? And that's pi over 2, pi over 2, pi, pi. So we may think about it that way, or y'all just plug it in your calculator. Plug in a number just slightly less than negative pi, so negative 3.2 is a little bit less than negative pi. Make sure you're in radian mode, and when you plug that into cosine, you're going to get a negative number. When you plug that into sine, you're also going to get a negative number. And you know what? I had to think about that further. You're not going to get a negative when you plug it in sine. You're going to get a positive. Look, that's negative pi right there. To the left of that is positive. Again, your calculator will tell you that too if you don't want to waste all this analyzing time. Now, overall, a negative times a negative is a positive divided by positive is a plus infinity. Okay, so our behavior as we approach negative pi from the left side, we should be going up to plus infinity on our graph. Now let's do this again. This time I'm going to plug in a number a little bigger than negative pi. And when I plug that into x, I still get a negative number. Okay, a number really close to negative pi is still negative. When I substitute that into cosine of x, okay, here's cosine on top here. Look, far right of the screen and look it on top. If I'm going to negative pi, which remember is right here, okay, then I'm talking about a negative value. All right, or plug in negative 3. That's to the right of negative pi. And then I plug that into sine, okay, that's going to give me a negative value. And all these negatives overall give you a negative infinity. Now let's take a look at this weird case in the middle, okay. Listen, if you plug 0 into this, okay, you get 0 over 0. Remember, that's a bad situation. Now see, if I plugged in negative pi into this situation, I do not get 0 on the top and 0 on the bottom. But this, when you plug in 0, and this is what makes this problem a little bit weird, you get 0 over 0. Now, you remember what that means when we took limits. That means this function somehow needs to simplify to calculate the limit as x goes to 0. Well, let's see what we can do with that. So I'm going to write it down. X times the cosine of x over the sine of x. Now you may recognize that. What if I move that sine of x over here below the x and rewrite this, and because I need space I'm going to erase. Let's take a look at this as cosine of x times x over sine of x. Do you remember what that limit was? When we go take the limit as x goes to 0 of x times the sine of x, remember that was equal to 1. And then I can plug in my 0 value. So when I take the cosine of 0 times that limit of 1, well, cosine of 0, okay, is 1. 1 times 1 is 1. So instead of it being plus or minus infinity, because this was a 0 over 0 situation, which these are not, by the way, okay, then I get a limit value of 1. And that's kind of weird, right? You know what that means? The function is undefined at 0, but the limit value is 1. That means we have a hole in the graph right here. Okay. Now, when I take the limit as x goes to 0 from the right, it's the same story. Okay, because we're looking at cosine of x times x over sine of x, and we had that special limit property that said, and let me highlight for you exactly what I'm saying. The limit as x goes to 0 of x over the sine of x is equal to 1. Okay, so that part is 1. And then I'm plugging in 0 into this part, which also gives me 1 times 1, which is the same 1 we got right there. So again, if you have an undefined spot, but it has a limit, okay, and the limit from the left and the right match, which is what happens here, it means we have a hole in the graph right there. So that's something to look forward to, or not, or something to dread as you go through. We'll see. Now, for this third set down here, it's going to work like this set over here. Okay, the values could differ. We'll see. But what I want you to realize is if you took pi and you plugged it right into this function, that's not going to give you 0 over 0. Okay, that's going to give you pi times cosine of pi, which is going to be -1 over undefined, over 0. So that's undefined, which means our answer must be plus or minus infinity. We just got to figure out which. So when I plug in pi from the left, you're talking about a number a little smaller than pi, into x, that's positive, because pi is a positive value. If I plug it into cosine, now we've got to be careful. This is pi over 2 on the cosine graph. This is pi on the cosine graph. Remember, cosine around pi is a negative value. Okay? Sine around pi, on the other hand, though, is going to 0, but from the left side, it's positive. So this simplifies to negative infinity. So when I look at my graph, as I approach pi from the left side, my graph should be going down to negative infinity forever. Now on the right side, I plug pi into x. That just gives me a positive number. I plug pi, a little bigger than pi, into cosine. That's going to give me a negative number. And I'll plug in a little bit bigger than pi into sine. That also gives me a negative number. You're talking about third quadrant situation. And that's going to simplify to positive infinity. Now I know that's a lot of work finding the behavior of the graph at every one of those asymptotes. Okay, but we learned from this, important, that turns out 0 is not even a vertical asymptote. It looked like one for a minute, because the function was undefined there. But we found out by checking out the behavior of the graph that actually we get a limit value. We don't get plus or minus infinity, and you don't get plus or minus infinity whenever you have 0 over 0. You must use some simplifying process, and when you're talking about a trig functions, it's one of those special limits that we learned about. Okay, now how about a horizontal asymptote? Now remember, help me remember how you find those, right? You take the limit as x goes to infinity of your function, of x times the cosine of x. But y'all, that kind of, to me, doesn't make any sense, because we're only looking at a domain of -2 pi to positive 2 pi. So there is no horizontal asymptote to deal with in this case. Okay. Not only that, when you plug infinity right here, you do get infinity times the cosine, which is just equal to infinity. So either way, there's either no horizontal asymptotes, or you consider the fact that you're only looking between -2 pi and positive 2 pi. So going out to infinity doesn't even make any sense. Okay, and a slant asymptote. Now remember, that happens when the degree of the numerator is 1 more than the degree of the denominator, when you're dealing with a trig function. And I'm sure there are trig functions that exist that probably have some kind of slant asymptote going on, but that's not what we're dealing with here. Okay, so this guy does not have a slant asymptote. All right, I think we're ready to move on to the first derivative. So to do the first derivative chart, remember in the chart we're trying to determine increasing, decreasing, relative max, relative min. And to do that, we need to take the first derivative. So here I go, g primed of x. Okay, so I need to take the derivative. This is a product rule, folks. So I've got first, second. So I take the first. Now, what's the derivative of cotangent of x? That's negative cosecant squared of x, right? Remember, all the co-derivatives are negative, so negative cosecant squared of x. So that's first over the second, plus the second, which is cotangent of x, times the derivative of the first. So the derivative of x is just 1. So that's our derivative. Now, remember what we have to do with our derivative. We have to find out where it's equal to 0 and where it's undefined. In other words, critical numbers. We've got to go find the critical numbers. Now, when I set this equal to 0, this first derivative, I really need it to look a little bit better than that. So you may want to go back in. I'm going to do this in red. G primed of x. Let's make it look better. Okay, first of all, the negative is going to be out front. And you may want to think about cosecant squared as 1 over sine squared, right? So this is equivalent to saying negative x over sine squared of x. You comfortable with that? That looks better to me. And then cotangent of x times 1 is just cotangent of x, also known as cosine of x over sine of x. So there is our first derivative. Now, remember, you got to set this thing equal to 0, so you may even want to go through the extra work of combining that fraction together, because I've got to solve this equation. And the easiest way to solve a trig equation is if, in fraction form, if it's a single fraction. Okay, so that's my advice, is write this as a single fraction. Well, what do I need to do that? A common denominator. So I'm going to multiply by sine of x over sine of x, right? So they both have a sine squared of x. That results in negative x plus cosine of x times sine of x over sine squared of x. So y'all, there is my first derivative. Okay, now there's, again, many different ways to write it, but it seems to me that writing it in terms of sine and cosine would make it easier to solve the equation. And next, having it as a single fraction like we do there. Okay, so now I'm going to set that thing equal to 0. So here we go. I've got 0 equals negative x plus cosine of x times sine of x over sine squared of x. Now here's where this gets fun, right? For a fraction to equal 0, you know the numerator is equal to 0. Or you just multiply both sides by sine squared of x, and that's going to give you 0 equals negative x plus cosine of x times sine of x. Okay? Now this is a weird problem. You may not be used to solving trig equations where you have part trig and part algebra like we do here. I'm going to add the x over. To me, this is a problem that we need to think about, okay? And we're thinking about cosine of x times sine of x is equal to x, okay? Now, I do know that when x equals sine of x, when you have to solve that equation, one of the solutions is x equals 0. But the problem, remember, with x equals 0 is the original function is not even defined at 0. So that does not count as a critical number. Not only that, this derivative is not defined at 0. Y'all, if you plug in 0 for sine of x right here in the red, you're going to get a 0 in the denominator. Sine of 0 is 0. So x equals 0 is the place where it's undefined, but the original function, again, is not defined there. Now, I think more about solving this, and you might have to resort to numerical methods to solve this, but if you think about, if you multiply cosine values times sine values, are you ever going to get the original x you plugged in? Like cosine of 0 is 1, so you don't get 1. You could think about it for a while, but there are no solutions to this equation, and that makes this problem tricky. It doesn't make for a good test question because solving the first derivative equal to 0 is just a booger because you have trig and algebra mixed up together. But numerically, you could graph y equals x and graph cosine of x times sine of x. I guess I could take a second to do that for you, and we can see what kind of results we get from that, and that could be our critical number. Let's take a look at that. Again, this is above and beyond, but we need to check it out. Okay, folks, here's what I did. I pulled up Desmos. I've got kind of a minimal view here for you, but notice on the first line at the top of the page on the left, I typed in cosine of x times sine of x, and that's the red graph that we've got going on, right? And then I typed in x. Now, you know when you solve an equation, you're just finding out where those two graphs intersect each other. Notice the only point of intersection is right there in the middle where the dot is at 0, and that's the one that we found. But I don't have an algebraic way to help you solve that. That's not something I've ever run into. I'm doing this graphically and just thinking about it numerically. But the 0 that we found a few minutes ago that we had to throw out is really the only solution to this equation. So the good news is we don't have any critical numbers whatsoever for this first derivative. So let's go back to our work and finish up. So here we are back to our work, and a little side tangent just to solve this equation, and we found out we have no critical numbers, none. So no critical numbers, which means when we do our table, what do we include? Well, remember that they only want us to look between negative 2 pi and positive 2 pi. And we still have to remove where the original function is undefined. So let's go to another page and complete this chart. Not only that, I need to make sure that I have my first derivative, this guy right here, accessible. Okay? So negative x plus cosine of x times sine of x over sine squared of x, or you could go back to this one. But remember, we're trying to find out if the first derivative is positive or negative. All right, here we go. I saved you a minute. So what I did is I recopied the derivative, negative x plus cosine of x times sine of x over sine squared of x. I listed our intervals. Where did I get these intervals values from? Remember, negative pi right here, 0, and positive pi are the places my original function right up here is undefined. We had no critical numbers, so I'm only looking at the intervals this original function is defined on, and we still have to use those undefined places when I test my points. Now, I'm trying to find values to plug in, so I need a value between negative pi and negative 2 pi, and we could use negative 3 pi over 2, if you like. And I need a value between negative pi and 0, okay? So a value between negative pi and 0 would be, say, negative pi over 2. And a value between 0 and pi would be positive pi over 2. And a value between pi and 2 pi might be 3 pi over 2. Now remember what I'm doing. I'm taking those values and I'm substituting into the first derivative. Now, y'all, there's nothing wrong with using your calculator. Please make sure if you use your calculator that you are in radian mode, because these values that we're plugging in are in radians. You could even select decimal test points rather than these unit circle values that I selected. But here I go. I'm going to figure that out. Now, when I typed that in, I had to do the actual number crunching. Okay, so you have negative, right, of a negative 3 pi over 2 plus cosine of negative 3 pi over 2 times sine of negative 3 pi over 2. See, look how big this is getting, all over sine squared of negative 3 pi over 2. Okay? Now, what happens is that ended up being 0 right there. Why? Because cosine of negative 3 pi over 2 is 0. Now, that's positive, so I got a positive in the numerator. Listen, the denominator's got to be positive. Why? Because it's squared. So overall, that gives me a positive value, and that means that I am increasing on the interval negative 2 pi to negative pi. So that's how I'm running the show, right? So now I'm going to do this for negative pi over 2. So I'm going to do it over to the right, though. So I've got negative of a negative pi over 2 plus the cosine of negative pi over 2 times the sine of negative pi over 2 all over something squared, which is positive. Now, cosine of negative pi over 2 is 0, so that whole term is 0, but a negative of a negative pi over 2 is positive. So this is a positive divided by a positive, which is a positive. Okay? Now listen, if that doesn't make sense, stop it. Pause the video, plug these values either in your calculator or crunch those numbers a lot slowly yourself so you really see what's going on. Because I'm just kind of waving my pluses and minuses all over the place because I see it. Okay, but you need to take the time so you see it yourself. I'm going to do the same thing for pi over 2. So watch this. I'm doing negative pi over 2. The negative, remember, is in the derivative. I'm plugging in pi over 2 for this x. Plus the cosine of pi over 2 times the sine of pi over 2 divided by something squared is always positive. Unless it's 0, but remember, we're not plugging in values that give us 0. Okay? Now, negative pi over 2 is negative, plus cosine of pi over 2 times sine of pi over 2 is 0, because cosine of pi over 2 is 0. So this is a negative divided by a positive, which is overall a negative value. So the interval before we were increasing, and now we are decreasing. I got one more of these to do, okay? So I've got negative 3 pi over 2 is what I'm plugging in, plus cosine of 3 pi over 2 times the sine of 3 pi over 2 over something squared, which is positive. Now, cosine of 3 pi over 2 is 0, so I've got a negative on top divided by a positive in the denominator, which is overall a negative, so we are decreasing on that interval. Alright, so we found out they were increasing at negative 2 pi to negative pi, increasing negative pi to 0, but notice it changes to decreasing on 0 to pi and then decreasing again. So what does that mean? Well, if you go from increasing to decreasing, the first derivative test tells us we have a relative maximum. But then you've got to remember that this function is undefined at x equal 0. Remember, we talked about that. Now at x equal to 0, though, we have a hole in the graph. So it looks like a relative max, more than likely, but there's actually an open circle right there where we would have a relative max because the function is undefined at x equals 0. So this is a pretty interesting graph. Now let's take a look at the second derivative, which, warning, right now, it has its own issues. Now, you remember the second derivative tells us where the function is concave upward if the second derivative is positive, or concave downward if the second derivative is negative. It also gives us inflection points, which is where the function changes concavity. So let's first, we've got the challenge of just taking the second derivative. So what I've done is I've put the first derivative, the original first derivative that we found. So we took that, remember, and changed everything to sine and cosine, so we could easily set it equal to 0 and find out where it's undefined. But now to take the derivative, we may want to look at this one, the more simple version, so I can just take the derivative. Now still, the second derivative is not going to be simple because look, this first term, I've got to use the product rule, where this is the first and this is the second function. And then I'll have to take the derivative of cotangent of x separately. So here we go. The derivative, and I wrote f prime of x, that's actually g prime of x, right? So g double prime of x, in other words, the second derivative, is the first, which is negative x, times the derivative of the second. Now, when I take the derivative of cosecant squared of x, here's what I'm imagining. That's cosecant of x all squared, right? And I have to use the chain rule. So the 2 is going to come in front. I rewrite cosecant of x, reduce that power by 1, so now it's to the first power, times the derivative of the inside. And we know the derivative of cosecant of x is negative cosecant of x times cotangent of x. Y'all, that's just the first times the derivative of the second. Plus, now I'm doing the second, which is cosecant squared of x, times the derivative of the first, which is -1. All right, so again, this is the second times the derivative of the first. Then I have to move on to cotangent of x, and we know the derivative of cotangent of x is negative cosecant squared of x. Now, this is quite a mess. We can clean it up some. Okay, so g double prime of x, in other words, the second derivative. Now let's make this look neater. Notice in this first term right here, all that is multiplication, right? So I have a negative x times 2 times a negative. So that's going to be 2x. And I have a cosecant of x times a cosecant of x. So that's going to be times cosecant squared of x times that cotangent of x. So make sure you're comfortable with that. Again, a negative x times 2 times a negative is going to be positive 2x. This cosecant times this cosecant is cosecant squared, and then there's my cotangent. Now this term we can rewrite as negative cosecant squared of x, and this term is also negative cosecant squared of x. So simplified a little bit more gives us 2x cosecant squared of x times cotangent of x minus, again, like terms right here. So there's two of those. So minus 2 cosecant squared of x. Now that is our second derivative. But keep in mind, what do we have to do with the second derivative? We need to know where that thing is equal to 0. And we also need to know, I'm going to put it way over here, where it is undefined. Both of those things. Now, these are going to find potential inflection points for us. Okay? So, first of all, I set this equal to 0. Now, y'all, to do this, I need this factored, if at all possible. So I think I'm going to erase and back up just a little bit and factor this. Now, when you're looking at this, this is a term and this is a term. What do those terms have in common? They have a 2 in common, and they have a cosecant squared of x in common. So let's factor that out. So I have g double prime of x is equal to 2 cosecant squared of x. All right, and then that leaves me with, so again, I pulled out the 2, I pulled out the cosecant squared of x. There's still an x times cotangent of x minus, now I pulled that entire thing out, right? So minus 1. And remember, what we're trying to do is set that equal to 0 and find out where it's undefined. So what I'm going to do is put equals to 0 right over there on the side. Now, if I set 2 cosecant squared of x equal to 0, we don't think in terms of cosecant, do we? At least I don't. You may. So that's going to be 2 over sine squared of x equal to 0. Now, y'all, that just can't happen, right? If I have a fraction equal to 0, there's no way in the world that's ever going to equal to 0 with a constant in the numerator. I can't turn that 2 into a 0. Okay, so at x equals 0, I'm going to move it over here on the undefined list. We know this part of the factors, okay, of our second derivative, that factor of the second derivative is undefined. But I can't set it equal to 0, so I don't get any solution for that factor equal to 0. Now this next one, I'm going to warn you right this minute, this one's a little bit frustrating. So watch this. I'm setting x times the cotangent of x minus 1 equal to 0. Okay? Now, I'm trying to solve for x. And I'm going to go ahead and present to you, there's an issue when you solve a trig function for x, if part of it's a trig function, like the cotangent of x, and part of it's just algebraic, like the x, okay? That's going to cause us a problem. But I'm going to attempt to get the cotangent of x isolated to help us think about this a little bit, okay? So I'm going to add the 1 first, and then divide by x. Now, dividing by x is a little bit of a dangerous thing, because when you divide by a variable, you're dividing by the possibility that x could be 0, right? And you can't divide by 0. But we already know the function's undefined at 0, so 0 is already thrown out of the mix, so we're not going to be concerned about that. Now watch this. What do I get if I take the reciprocal of cotangent? Flip it upside down, right? That would be tangent of x, flip that guy upside down, equals x. Now, we can't just take the inverse tangent of both sides because I have x's on both sides. Remember, the goal always is try to get your x's on the same side of the equation and factor, or take the inverse function. But listen, there's no way I can move that x out of there and include it with that x over there. This is a strange problem, and it's a problem that requires what we call numerical methods, which means we don't have a way to solve this easily. But now there is one solution that may be pretty obvious. If I let x equal to 0, that would work. And so you could see that tangent of 0 equals 0. So this is just a guess, okay, that x equals 0 works, and it does. But remember, our function is undefined at x equals 0 anyway. It's really already on our list of intervals, our list of numbers to split up the interval. So, but that does work. That makes this equation true. But the thought is, do any more values make the equation true? Okay. Now the quick story behind that is whenever you're presented with an equation that has no technique to solve it, and listen, there are plenty of equations that have no regular algebraic technique to solve it, you could consider the graph. If y'all remember what tangent looks like, it does this, like repeatedly, right? Forever and ever and ever and ever. I'm not trying to make an exact graph. Now, what does x look like? I'm going to graph it in red. Well, it looks like that. I didn't do such a good job of that, okay? But we can tell that there's that x equals 0. They intersect there, but it's also possible that x and your tangent intersect here and here, and then again here and way down here, and then again here and way down here. It turns out they intersect an infinite number of times. But we don't care about that. We care about where it intersects on the interval from -2 pi to +2 pi. So we've got to do something we don't normally do. Let's look at a well-graphed version of this in Desmos and see if we can't find those solutions. Now, this is not a typical problem. Please don't roll your eyes or sigh loudly, please. This is not a typical problem, and this is one reason I want you to see this problem, because it is not a typical problem. But let's see what we can do to find critical numbers for the second derivative and solve tangent of x equals x. So I'm going to pull up Desmos, okay? All right, so here I am, I'm in Desmos, and remember what we're trying to solve is tangent of x equals to x. So I'm going to type in y equals tangent of x, and you recognize that, right? And I'm going to type in y equals x, and I'm going to find out where they intersect each other. Now take a look. Remember, I can't write on top of this, but I can use my mouse to circle. Look at there. That is one of my solutions if it fits in my interval. Now there's that 0 solution where they cross each other. How many times do they cross each other? Forever. Here and here, an infinite number of times. Look, it'll do it here. I could zoom out and you can see many more times. Look at there. Everywhere there's a gray dot, that is an intersection between tangent of x and x. Which, remember what we're trying to do, we're trying to find critical numbers for the second derivative. But now I'm only looking between -2 pi and +2 pi. Now I could help ourselves a little bit here by, let me scoot back out, and I'll hit the tool and I'm going to change my x-axis to -2 pi, and I just type in pi, lowercase pi for pi, to +2 pi. And then I'll see what kind of answers I have. Is it just 0, or do I have more than that? Okay, well, there we go. Now, there's my 0. Remember, our original function was undefined as 0 anyway, so we don't have to worry about that, except it still needs to be on our table. But look, there's another one. Now, what is that value? If I could click on there, oh, look, it told me 4.493. Okay, the x and the y value, because remember it's on the line y equals x. So 4.493, remember that because I got to write it down. 4.493, and then there's not another one to the right, and then look right down here. Negative 4.493 is the other critical number for the second derivative. Now again, this is unusual. We're used to using algebra techniques to solve the derivative equal to 0. This is just a kind of a freak problem. But I thought it worth it to show you this freak problem because they put it in the homework, so there it is. Let's go back to our work and then remember 4.493 and negative 4.493. Alright, so remember we've got x is equal to negative 4.493 and x is equal to positive 4.493. And again, that was not found with algebra, that was found with numerical methods by just simply looking at the graph, and thank goodness for Desmos, because wow, that would be quite a challenge. So now I'm going to go to the next page and we're going to do a chart for this to finally wrap up this problem. Okay, so I did a little bit of work while it was paused for you. I copied the second derivative at the top of the page because we need that. And I split our interval up. Remember, the original interval went from negative 2 pi to, I left off an interval, to positive 2 pi. So this is 4.493. And then my last interval is 4.493 to 2 pi. I have to squeeze it in. So let's recap. We went from negative 2 pi to negative 4.493. Okay. Negative 4.493 to negative pi. Negative pi to 0, 0 to pi, pi to 4.493, and finally 4.493 all the way to 2 pi. Now, test interval, okay, or test point in the interval. Now, you could, negative 2 pi is just negative 6.28. You could just plug in like negative 5 if you want to. Or you could plug in negative 7 pi over 4, which is a value on the unit circle. Listen, I'm good with either one. If you're using your calculator, don't feel like you have to use these radians. Negative 5 would work. Something between negative 4.493 and negative pi might be negative 5 pi over 4. How do you really know? I mean, you can type in 5 pi, doing it right now, divide by 4, and that gives me negative 3.9. So I know it fits in there, right? Now, value between negative pi and 0 would be negative pi over 2. We got that. Positive pi over 2 for 0 to pi. Positive 5 pi over 4, 4 pi to 4.493. And finally, 7 pi over 4 for that last interval. So I just did the positive and negatives of the same. Okay? Now, here's what I know. Looking over here, this, I don't care what you plug in, is going to be positive. How do I know that? Because anything squared is positive unless you're plugging in something that gives you 0, but you're not, because those are critical numbers. You don't want to plug in things that give you 0. And that's what these intervals are all split up for. That's the entire reason we split them up. All right, so I'm not plugging in 0. That means any number I plug in is going to turn positive. So this part's positive. This part over here, highlighted in green, we're going to have to calculate every time. You know why? Because we take x times the cotangent of x and subtract 1. We can't just multiply and say that's going to be positive or negative because we're subtracting 1. All right, so we got a little bit of number crunching to do, but we can do it. All right, so I've got a positive because of the yellow part. But then I have to do negative 7 pi over 4 times the cotangent of negative 7 pi over 4, and then subtract 1 from that. Now, y'all, honestly, I would plug this in my calculator, or either plug in negative 5. That works too. You need to be in radian mode to do that. Okay. Now, here's the way I'm going to think about it. Still, though, you'd have to do a lot of calculating. Let's don't do that. I'm just going to crunch these numbers in my calculator. I'm going to plug in negative 5. I don't think I just want to do all this number crunching. Y'all, a calculator will do you good. Right here, something between negative 4 and negative 3.14 would be negative 3.5. That's better, decimal. Something between negative pi and 0, okay. Maybe negative 2. something between 0 and pi, positive 2, something between pi and 4.493. Well, pi is 3.14, so 3.5 would work, or even 4 would work. I don't know why I didn't pick negative 4 here. That would have been fine. Let's do that. Negative 4 and 4. And then positive 5 would work here. I'm going to pause it. I'm just going to plug these numbers in my calculator and tell you the exact value I get, okay? Actually, I'm not, because this is positive. I'm wasting time. All I'm going to do is plug it in here and tell you the exact value I get. Okay, folks, I'm back. I'm not going to lie, that took a few minutes. So, again, you could use these radian values, but I found out that I just don't think it's worth it. As long as you pick some values between these intervals, whole numbers are fine. Please make sure you're in radian mode in your calculator. And the calculation I did on the first one, I plugged in negative 5. So again, this I assumed is positive because it is, no matter what. I didn't crunch numbers for that guy. I did for this because I did negative 5 times cotangent of negative 5 minus 1. In your calculator, you got to be careful. You don't have a cotangent button. You have to do tangent and then flip it upside down. Okay? In other words, that x to the negative 1 button will work for you. See if you don't get that value. Now, a positive times a negative overall is a negative. So what does that mean? This is concave downward. Okay? Now, here I plugged in negative 4. Again, my calculation that I did is negative 4 times cotangent of negative 4. Then I subtracted 1. But really in my calculator, I calculated tangent of negative 4 and took the reciprocal. Then I multiplied by negative 4, and then I subtracted 1. And that gave me a positive 2.455. A positive times a positive overall is a positive, so this is concave upward. Alright, my next value, I plugged in negative 2, because negative 2 is between 0 and negative pi. Remember, negative pi is negative 3.14. So that's going to be negative 2 times the cotangent of negative 2, subtract 1. Again, I calculated the tangent of negative 2 first. I took the reciprocal of that, multiplied it by negative 2, and then subtracted 1 in my calculator, and that gave me negative 1.91. But a positive times a negative is overall a negative, so we're back to concave downward. Okay? Plugged in positive 2. Again, I assumed that 2 cosecant squared of 2 is positive, so that's what this first positive is about, is that one every time. The next positive is where I plugged it into the green, so I said 2 times cotangent of 2 minus 1. To do that calculation, I did tangent of 2, took the reciprocal, multiplied by 2, subtracted 1, and I got another negative 1.91, and that positive times a negative is a negative. By now you know what I'm doing, so I plugged in 4, I plugged in 5. Positive times positive is a positive, and positive times negative is a negative. What does that mean? We are down on that interval, we are up on that interval, and we are down on that interval. Phew! Now what we want to do is put all this information together, and it is a lot, to see if we can't come up with a reasonable looking graph. Alright, so here I have, I think, everything summarized. It is a lot of information, but remember our function was undefined, our original function at negative pi, 0, and pi. So we talked about that when we talked about domain. The x-intercepts, and why this is underlined, I don't know. It's some weird formatting thing y'all couldn't get rid of. But anyway, we had x-intercepts at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Now notice my scale right here doesn't have radian values, so you might want to think about those in terms of decimals when you think about negative 3 pi over 2. So I'm doing 3 times pi and then dividing that by 2. That gives me negative 4.7. So here's negative 5, so negative 4.7. We have an x-intercept about right there. And then one at negative pi over 2. So a lot of you know what pi divided by 2 is, but 1.57. So that's negative 1.57 right there. So there's negative 1, about negative 1.5. Remember, this is an approximation. Pi over 2, so 1.57. And then 3 pi over 2, again, that's going to be that positive 4.7, almost 5. Those are my x-intercepts. Okay, y-intercepts, we don't have any. Vertical asymptotes, okay, we have one at negative pi. Remember, that's negative 3.14, so there's negative 1, negative 2, negative 3. Then you're going to do it just barely to the left of negative 3. So I have a vertical asymptote there. I'm struggling making a decent looking dashed line. Let me try that again. It's a little better. All right, and then also at positive pi. So again, 1, 2, 3, and slightly to the right, because we're talking about 3.14. All right, now, horizontal asymptote, remember we talked about that. We're only looking at the interval negative 2 pi to 2 pi, so we're not going out to infinity in both directions. Slant asymptote, we didn't have one. Notice we're increasing from negative 2 pi all the way to negative pi. So over here we're increasing, okay? And we could go back and look at the behavior of the asymptote. If we're approaching negative pi from the left, it should have been increasing, okay? Is that right? Is that what we have? Let's go read. I had to just make sure that felt weird, y'all. So I did. We're increasing over that whole interval. Not only that, notice that we're concave downward for negative 2 pi to that 4.493. Maybe we should plot those inflection points. Remember when it changed concavity? So negative 4.493 to 1. So negative 4.4. So there's 1, 2, 3. There's negative 4.4 and a little more, and up at 1. That's where my graph changes concavity. So it's concave downward on this side, and then it flips to concave upward on this side. And it approaches positive infinity to the left of negative pi. Okay? Now that's weird. So this is going down, but this is not a vertical asymptote, so it kind of just falls off the graph. Now, let's see what's happening in between here. Okay? So I know I have intercepts right here. What about increasing, decreasing? So we're increasing from negative pi to 0. Okay, so I'm going up from negative pi to 0. Okay, now remember that we have a hole in the graph. Remember way back when we had a hole in the graph? And let me scroll back so you can see that. Is that the page where we talked about the hole? There it is. We have a hole in the graph. Our limit value is 1 at 0, but our answer is not 1 at 0. So let's put that hole in the graph too. That'll help. There's a hole right here, folks. So it goes up to that hole, but then it doesn't touch. Okay. Now on the other side, between 0 and pi, because remember this is pi over here, a vertical asymptote. What's happening? Okay. Well, between... that says negative 0. Y'all just ignore that, please. That's 0 to pi. We are decreasing, so it's going down. Look, it matches what we're saying. We could also find the behavior between 0 and pi is going to negative infinity. We could go back and look at the behavior there. Okay. And then on the other side, what's going on over here? So between pi and 2 pi right here, we're decreasing. So my graph is going down from left to right. Not only that, the concavity, what's going on there? Well, concave upward, okay, between pi and 4.493. So this is concave. So between pi and 4.493, we're concave upward. So it flips up, and then... oh, and I forgot to plot that point. It doesn't change concavity there. Hold on. It changes concavity at that point, the inflection point, 4.4931. Okay, so 4.41, about here, is where it changes concavity. So it's concave upward, and then it flips to concave downward. Okay, and then it crosses over here somewhere and goes down. Whew! Now, let's check some other stuff. Okay, we've got our inflection points plotted. They showed up down here where the graph changed concavity. Are we concave downward where it says from negative 2 pi to 4.493? That's this part. That's concave downward. Okay. Between negative pi and 0, that's definitely concave downward. Between 0 and pi, notice that's also concave downward. And then once again, from 4.493 to 2 pi. Well, my graph's a little wonky, but that's concave downward right there. And then it's only concave upward in 2 places. I'll highlight in blue right there and right there. Okay. And then relative maximums. Notice I have none. Now, I would have had one right here if the function were defined right there, but it's not. This was fun, wasn't it? Please don't be frustrated with me. I really wanted you to see this disaster of a problem. It is number 44 in the homework, so it does really exist. I know all trig functions are not that bad. We'll do some in class that are easier, but I just wanted you to see this, okay? You want to see the Desmos graph? Would that make you feel better? Hold on. Woohoo! There it is. There's the Desmos graph. Now, what's wrong with the Desmos graph? Okay, well, first of all, I'm not in Desmos. This is on my paper, so I could draw on this. It's on my PowerPoint. But look, Desmos doesn't show us that that's undefined. But that is undefined. Why does it have extra stuff? Because I didn't restrict the domain. I wanted you could even go out further, and this repeats forever in both directions. We were only looking between negative pi, remember negative pi is, negative 2 pi, my bad, is 6.28 negative. So about here is where our graph started, okay, to positive 6.28, so about right here is where it cuts off. I just wanted you to see the rest of it. So we got it. We did it, but boy was it challenging. Okay, well, ask me your questions in class. I hope you have a wonderful day.